One of the reasons we spend so much time talking about exponents in our math classes is because they have so many applications with investments, so money situations, loans, and also things that are growing or decaying in nature. So populations that are growing, bacteria, and things that are decaying too, like carbon dating, anything that is radioactive and is decaying over time. Those are all going to be modeled with exponential functions. So two functions that we have worked with before is we have a formula for compound interest, and we dealt with that not too long ago. So if you want to find the compound interest, P is your principal, R is your rate, N is the number of times you compound per year, so quarterly or monthly, and then T is your time. One thing that I do want to point out is when you put this into your calculator, you need to have your exponent in parentheses. Otherwise, your calculator is going to tell you very strange things. Now, if it's something that compounds continuously, so we're not calculating our interest every month or every day or even every hour, we're continuously compounding it, that is the PERT equation, and it uses that irrational number E. So let's take a look at some examples. We're investing $6,000 at an annual rate of 4%. We want to find the balance after 7 years. So first, we are compounding interest quarterly. So that's going to be that first formula. The amount that we have is our principal, which is $6,000. Our rate is 4%. Make sure you write it as 0.04, otherwise you're going to get ridiculous answers. Quarterly means 4 times per year. And 4 times, we're going to leave it there for 7 years. So that is exactly what you're putting in your calculator. You can put it in exactly how it appears with the parentheses, and you should get $7,927.75. Always round these to the nearest cent. We're talking about money. All right, if instead we compound monthly, we're going to use the same formula. And everything's the same except for instead of doing it quarterly, we're going to do it 12 times a year, monthly. Still leaving it there for 7 years. So put that all in your calculator. You get 7,935.08 cents. And then if we're compounding continuously, now we're going to switch formulas. We're going to go to PERT. So our principal is still 6,000. Times E, remember E is just a button on your calculator, and it's going to automatically start parentheses. The rate is 0.04 times the time, which is 7 years. Sorry about that 7, that does not look good. And you should get 7,938.78. So notice the more frequently the interest is compounded, the more money you make. It's not a ton more. These should all be very similar answers, but notice they do get bigger the more we compound. Also, if you get something ridiculous, like if all of a sudden you have $2 million when you invested $6,000, please go back and make sure you put it in your calculator correctly. Just remember, it's an investment. It's not a miracle. All right, so in 1986, there was a nuclear accident in Chernobyl. You should probably heard about it before. It was in Soviet Union, which is now Russia. So it spread highly toxic radioactive chemicals, primarily plutonium-239, over hundreds of square miles. The area was evacuated. It's still not inhabited to this day. So this is the model that represents the amount of plutonium that remains. There was originally 10 pounds. So we want to know how much plutonium is there today. So let's see. Today, the amount of plutonium is 10 times 1/2. You're going to need to put this in parentheses. So our time since 1986. So let's see. Is that 34 years? Does that sound right? I think that sounds right to me. So 34 divided by 24100. Okay, Need a calculator for this. So let's find our calculator. So when I put that in, 10 times 0.5 to the parentheses, 34 divided by 24100, we find that we still have 9.99 pounds. So a little bit's decayed, not very much. All right, we want to know how much will remain in the year. I don't know why that says 2089. Let's find 2086. So 100 years after the accident. Okay, so in 2086, the amount of plutonium will be 10 times 1/2 to the 100 divided by 24,100. So we'll put that into the calculator. Just make sure you're using your parentheses appropriately. And we get 9.97 pounds. So still a lot of plutonium floating around. Okay, what about in 125,000 years? That seems like a while. So the amount of plutonium is going to be 10 times 1/2 to the 125,000 divided by 21,400. And in 125,000 years, we finally have made some progress. We have 0.27, not grams, sorry, pounds. So this type of plutonium decays very, very slowly. It is going to be there for a long time. Chernobyl is going to be not a great place to live at any time in the future. All right, so immediately following an injection, the concentration of drug in the bloodstream is 300 milligrams per milliliter. And after T hours, the concentration is 75% of the level of the previous hour. So we want to find a model for the concentration and then use it to find the concentration of the drug after 8 hours. This is another great example of ways that we use our exponential decay because our body is absorbing this drug, utilizing it for whatever purpose. So we want a model for this. It's the concentration in terms of time. So we definitely started with 300. And then after an hour, there's 75% of that left. So we would multiply 300 by 75%. And then after another hour, there's 75% of that left. So we would multiply 300 and times it by 75% again. And then after another hour, we would multiply by 75% again. So we are multiplying by 75% t times. So it's going to be 0.75 to the t. So that's the model. And then they want us to find the concentration after 8 hours, which means we are just going to plug in 8 for T, put this into your calculator, and you should get 30 milligrams per milliliter.